Hi, welcome again to another session of the tutorial. So today we're talking about spherical lenses. Um, Lenses, they are actually the refractive medium too, just like prisms. But they are bordered by two curved surfaces, unlike a prism that has just two plane surfaces. So they are bordered by two curved surfaces which have a common axis. So that's how we used to define them. And how I used to think about is that hmm, lenses are present. You know, once you think about it like that, you understand why they are that. Lenses are prisms. That's why I always talk about prismatic effect of lenses. Lenses are prisms, but it's just the orientation of prism that differs. That's what kind of concave or convex lenses. Because the concave lenses that are like two prisms. Okay. I think let me just show you what I mean by lenses are prisms. So imagine you have two prisms like this. Two prisms base to base. I know that in general, the convex lens they converge, while the concave lens diverge. Okay. Now imagine you want to converge something. What do you think you will need? Okay, so this is what we are not talking about. You have two prisms like this. And these two prisms, the base are toward each other. Then you see the base are toward each other. These are the two prisms. The base toward each other, base facing each other. So again, when we talk about the base function by pacing, we always bring ray from that apex, from the base having. The ray we always bring all the image information we talk about is always from the along the base like this, of course, and then it's going to hit the prism. So we're going to move toward normal from the less dense to more dense medium. We're going to move toward normal and then hit this other medium. From the denser medium to a less dense, it's going to move away from the normal. Okay. Now, again, this we do the same thing for it because the prism is inverted, so we have to pick it from there. Because again, it's from the same base. Remember the base. So because it's inverted, that's why it's like that. So we also put this towards normal away from the number. Can you see that they are meeting? And that was the idea behind the convex lens. So it's two prism based toward each other. So you can now compete. Can you imagine? You just compete it like this. Just put it in a cycle. Does that not form a convex lens? Can see why a convex lens will converge. Decades. Can see why a convex lens will converge. Because if the medium is different, it's the same thing, not training. The same thing, but so if you put here, that means like here is there and then here is there. So if that one is equal, you can see convex lens will converge. And that's why convex lens will converge because it's like two prism base stacked to that toward each other. So the lens is a convex lens is two prisms actually based toward each other. So that's a convex lens. Now let's um let's imagine we have two prisms with apex toward each other. Okay. So let's complete the diagram. So again, it's from the base. Started toward normal. Away from the normal. From the base. Started toward normal. Away from the normal. Can see they are going separately. So that's why concave lens will diverge because actually two prisms are based to be at the apex to apex. Because apex is facing each other. So let me just complete it. Can see this is a concave lens. This is a concave lens. And it's two prism apex facing each other. So can you see that? So that is how to make a prism. So two prism based on each other convex lens, two prism appears toward each other, like appears to appears. That's a concave lens. So just like we did in the there are different parts of the lens too. We have the principal plane. So the convex lens, the principal plane usually is to represent the convex lens. So the convex lens are represented by this arrowheads. Those like this is the way convex lens is now, right? Right, convex lens. So you now pick that top. So that top lens, so what is to represent the convex? This is a convex lens. And this is a concave lens. Let me shorten this a bit. I can compare. This is a concave lens. Let's use that color. This is a concave lens. So anyway, you see this in optics. This is a concave lens. And it's because of this, the way the concave lens is, so they just bring that top and put it to the center. So that's the concave lens and that's the convex lens. Okay. All right. So the line that cuts across the center here with the principal axis. Okay. The center of the concave lens, the principal axis. Okay. And then this is the principal axis. Okay. The principal axis. Principal axis. So yeah, and then the point where the principal point goes out, the principal axis is called another point. And then and it's where the ray goes on the vector. So this is not that point. That point. That's where the rays go on the vector. So that's that about the path. So let's now move to specific definitions. The F1, the F2. So now what does the F1 means optically? And that's the converse lens. There's the perspectives. Right to fuck the problems too. Right, so some definition of time. F1 and F2, so F1. Now F1 is the point of, okay, let's just define it. It's the point of origin of rays. If you start striking the lens, it becomes parallel. So it's the point of origin of rays. So F1 for a concave lens that's located on this left side. Mathematically, this is like zero. Decades. Anything on the left side is a minus. Anything on the right side is plus mathematically. So now the point of origin of rays, which after striking the lens, it becomes parallel. So point of origin, where rays are coming from, you can see the rays are coming from here. Okay, that's the F1. After striking the lens, it becomes parallel. You can see where the rays are coming, they are divergent. And so the lens just make it parallel. So that's the F1. So it's the point of origin of rays, which after striking the lens, they become parallel. So that's the F1. You can see. When they become divergent. And then when they hit the lens, it become parallel. And that's the F1. For a convex lenses, it will be on the negative side, so it's minus. So F1 for a convex lens is minus. For a convex lens is minus, so it's negative. Now for a concave lens, because the F1 is actually a virtual point, so it's catchy. It's also the point of origin in this sense, actually. but this is how you draw that one. No, the rays for the F1 for the if you notice for the convex lens, the rays are diverging, okay, and they become parallel. Now for the concave lens, you bring the rays that are trying to converge so that they now become parallel. So it's like they're coming convergent like this to draw the F1 convergence. I see you told us what convergence is in the previous video. We go back and revise to check that um convergence. And once they hit the lens, become parallel. Now, what does that mean? The implication is that if it's actually did not reach the lens, it will have continued like that. So where it's continued to is what we call the F1. That's why I call it point of origin of rays, which after cycling the lens becomes parallel. So we're supposed to continue, but because the virtual point, that's why we normally put solid. We're supposed to continue like this because not the way that was convergent is extrapolate the way is that one that I now extrapolate back to reach the F1. Can you see? And so this is how to draw diagram. Very interesting. So it's the way that we're converging that you extrapolate back to the F1. So that the recent is actually like it's coming from that F1, then it goes parallel. Come from F1 goes parallel. And so the F1 for a concave lens is positive. Okay, it's a sign convention, 0 plus minus from the mathematics. So F1 for a concave lens is positive. So, so let's define F2. So that's F1 for you, right? Which is the diagram. The F2, if the F2 is a point in which parallel rays of light collect draw the lenses first. So that you get it. The sections are made sometimes made short so that you understand and then you will not be rushing this and then it can make you stick better. All right, so first option the concave lens to right. So now F2 is the point of convergence. It's the point in which parallel rays of light converge to or appear to diverge from. Do you get that statement? Where they converge to in convex lens or appear to diverge from in concave lens. So where you have parallel rays of light that are coming from infinity. Where they converge to, because the convex will converge. So where they converge to is a F2 for a convex lens. I mean, so according to side, always put your arrows again. If you put any line without arrow is line and it's not scored. So F2, like sign convention, this is positive mathematics. And so F2 is positive for a convex lens. Now, F2 is also for intuitive parallels of light appear to diverge from for working length because it's a negative length. That's why they are diverged from. So they are coming and then they diverge from as soon as they diverge. So when I start following those rules, so can you see? So the F2 is here. So the F2 of the concave lens is negative. So F2 for a concave lens is negative. So what determines the power of the lens is the F2, the second focal length. And so since the F2 is positive for a convex lens, the convex lenses are called plus lenses. Can you imagine? It's because the F2 is positive. That's why they're called plus lenses. And the F2 is negative for a concave lens. They are called minus lenses. That's why they are called minus lenses. So, and so that sums the introduction to spherical lenses. So the next one we'll be doing is image formation by the lenses. Thank you. So please, again, once the video finish, sit down, draw the diagrams again, let it stick in, let the evidence stick in, right? You apply it.